We are here at the meeting of the American Astronomical Society in Seattle, Washington. And today I'm delighted to be talking to Dr. Tommaso Treu, who is professor in the Department of Physics at the University of California, Santa Barbara. He is giving a lecture here, an invited lecture at the AAS meeting about supermassive black holes and dark matter. And we'll be asking him about all of this stuff today. Just before I begin, though, Tommaso, let me ask you. These strange objects that you study, these supermassive black holes, elliptical galaxies, dark energy, dark matter, how did you come to this in the first place? How in the world did you become an astronomer? Why the decision to follow this strange career path?
Oh, it's like, almost like in the movies. Mm-hmm. So ever since I was a little kid, I knew I wanted to do physics. Mm-hmm. And I think this was in second grade or something. Mm-hmm. There was a father of a friend of mine who was a physicist. He gave us this, elementary school level lecture on the standard model of particle physics. And I just loved it. I said, and that was it. I knew already that I was very good at math, but that was sort of and ever since then I wanted to be a physicist. Then for a long time I wanted to be a particle physicist. For a long time, meaning between the age of 7 and 16, maybe. And then
you weren't interested in girls towards the end of that.
No,
just
really. Quarks were.
That was it.
That was it. And then when I went to college, I decided that maybe I was more interested in astrophysics than in particle physics. Mm-hmm. I seemed like a more diverse field at that time. Right. I had a friend of mine who was doing grad school with me, and he was started working on an LHC, which is, great. Fantastic.
The Large Hadron Collider,
oh, yeah.
the enormous accelerator in Switzerland, France.
That was always for me the other option. Mm-hmm. But I don't regret it at all. I mean, astronomy is great. Mm-hmm. You get to see all these beautiful pictures and work with so many different experiments. Mm-hmm. You can work in small groups, big teams, and it's very stimulating.
So the subject of your talk is dark matter and supermassive black holes, two of the things that have perhaps most captured the imagination of the public. Tell us a little bit about both of them. First of all, tell us what dark matter is.
Well, we don't know. I mean, that's the good part. So nobody knows. So one of the most shocking discoveries, if you will, of the last 30 years maybe, is that most of the mass in the universe is in form of probably a particle, we don't know, but something like we've never seen on Earth.
So it's not electrons or protons
or
neutrons, it can't be.
It can't be.
Okay.
We know it's not this regular stuff that makes you and me or this wall, right. Nothing like that. Right. It's some other particle, some other thing.
But how do we know it's there?
Because it has mass, and when it has mass it creates gravity. Okay. So we can feel its gravitational pull.
But I don't feel it.
You do. Well, not on Earth.
Yes.
Because on Earth there's a strong gravity from Earth that is nearby.
Right.
But if we're floating, in outer space, your motion will probably be influenced by the distribution of this mysterious dark matter.
Okay, so it must exist in our galaxy too. It's not just far away in the universe.
It's everywhere. Of course, in a place like Earth, that is a very special place where mass is very concentrated with respect to the fluffy universe around us. Then we only feel the gravitational field from Earth. But if you were anywhere else in the universe, you would feel dark matter.
And how do astronomers actually detect the dark matter and prove beyond any shadow of a doubt that it exists?
Well, there are many different ways, and we have had several experiments that have told us that. One that I particularly like is the one based on gravitational lensing. That is the fact that when you have a big massive object in front of a light source, light rays from the background source get deflected by the big mass. Okay. And you can have what the French call a mirage, multiple images of the same background object. And those multiple images tell you how much mass, how much stuff there is in front of the light source.
So the very distant background object which is being miraged, or whose light is being broken up, is some very distant galaxy,
for example.
For example, okay. Yeah. And then the light from that is then bent. It's deflected as if it were going through a lens.
Exactly. That's why it's called lensing.
But it's not a glass lens.
No.
It is the gravity of the dark matter that is doing
Gravity
it.
is so strong that pulls light. As light goes by the object, it gets deflected.
As Einstein first predicted
Right.
back in 1919.
Exactly.
Okay.
And using this effect, we can show, I would say beyond any reasonable doubt, that there is more mass than meets the eye.
Okay. So it's not just the galaxies you
Right.
see, there's something much more massive there.
Exactly.
But we don't know what it is.
We have no clue. I mean, there are theories, of course, of what it might be,
Okay.
but we have never detected a dark matter particle yet.
And so if I take a flashlight, for example, and shine it across the room, this room here, there may be dark matter particles in the room, but somehow the light isn't scattering off those particles.
You need a lot of mass over very big scales to create this effect.
Okay.
So in this room, there's not nearly enough dark matter to create that effect.
So that's why we've got to study it on the grand scale of the universe.
So the way I see it is that when you study it on the great scale of the universe, you can tell how much of this stuff there is, where is it located,
Right.
how does it behave on large scales. And then we have to build big underground experiments to try to catch the one particle that happens to be flying through Earth at that particular time.
Okay.
And so it's only a combination of the two things that allows us to understand how much of this stuff is there in the universe and what it is.
Is then most of the universe made of dark matter, or is there something else that's even more of the 900-pound gorilla?
Yeah, so this part was shocking enough, right?
Yes.
But then it turns out that in the last decade or so, people have discovered that the universe is accelerating. So gravity normally...
The expansion of the universe.
Yeah, so the universe is not only expanding, but it's expanding faster and faster, that is accelerating.
Right.
And normally, we would expect gravity to slow down the expansion.
Right.
Like when I throw an apple up in the air, it will come back down. And it's like if the universe behaves as if I threw the apple up in the air, and the apple would start accelerating and go faster and faster upwards.
Somebody's got to be pushing it upwards.
Somebody's got to be pushing it upwards. And for lack of a better name, we call this thing dark energy. And this makes up most of the energy in the universe. So you have to remember that through Einstein's equation, energy and mass are equivalent. So and even though this dark energy may not have mass, it is still the dominant energy component in the universe. Makes up probably 3/4 of the mass of the universe.
Now, if it has energy, if there is energy, it also has mass. E equals mc squared, as you mentioned. But yes. But still, that energy must have gravity too.
Right, but it also has something that we don't really have a good analog in real life.
Okay.
There is something, we all experience pressure,
Right.
but there is something called negative pressure. And that's the mysterious exotic property that this dark energy has.
Right.
Has a negative pressure, and that is what pulls the universe and accelerates the expansion of the universe.
Now, I might believe your story about the dark matter.
Yeah.
Why should I believe your story about the dark energy? What is the evidence that astronomers simply are stuck with, are faced with, and despite their lack of initial belief in it, are still forced to believe in the dark energy?
So, and I would like here to take a minute to dispel a myth.
Okay.
It's not that we're all crazy and we're smoking strange stuff and we believe dark energy and dark matter because it's cool.
Right.
If we could, we would get rid of it, because there's nothing like coming up with new particles and fields that have never been seen in the lab. We hate that because it's like admission of ignorance. And so we're forced to conclude there has to be something like that from experimental evidence. So the main evidence is that the universe is accelerating. So people do different kind of experiments. A famous one is supernovae. People have looked at very distant supernovae. Supernovae are stars that explode, and under some circumstances they have a very specific luminosity. And so by measuring the apparent luminosity of these objects, we can figure out how far they are.
Just because they are really 100-watt light bulbs, very
Exactly.
standard candles.
It's pretty much like if we were saying I'm holding a 100 watts light bulb and I'm going further and further away, you will see the light get dimmer and dimmer, and you can figure out how far I am. And so in this way, people have figured out that very distant supernovae do not appear the way they should appear if the universe had been expanding at a rate that is slowing down.
Okay.
There has to be some acceleration. Of course, that doesn't, I mean, now I want to be a bit provocative. That doesn't mean that's the only explanation.
Right.
Maybe in 10 years' time, some very smart person comes up with a theory that explains it without acceleration.
Maybe we don't understand the supernovas well enough.
Exactly, but there are other pieces of evidence as well, like there's a cosmic microwave background and so on. So it's not just the supernovae, clusters of galaxies. There's several pieces of evidence. So at this time, it's hard to just say it's a fluke in one experimental method.
Right.
But maybe our own idea of the universe is wrong, and maybe we can explain what we see with a completely different framework that is not, your classic Big Bang general relativity theory. So that's something we have always to keep in the back of our mind.
So let's head towards the subject of your talk.
Right.
There's a component in there about elliptical galaxies. Right. Tell me what these things are.
So when you look up in the sky, with the naked eye, you don't see much in terms of distant galaxies. But if you just take any small telescope, you will start seeing different galaxies. And galaxies don't come in all forms and shapes and colors. There are very specific forms and shapes. Some of them are called spirals, like our own Milky Way, that looks like a spiral. And some of them are called elliptical because they look like big ellipses.
A football.
A football.
Well, an American football.
An American football, yeah, not a soccer ball.
That's right.
Yeah. And so these galaxies are extremely massive. They're probably the biggest guys around, they're typically, and they have very old stars.
And when you say very, very massive, what does that mean?
It means typical mass in stars is 1,000 billion times the mass of the sun.
Okay.
So they have like 1,000 billion suns in them. So they're pretty big guys.
Pretty massive.
Yes. And that's only, I would say, the part that you can see. Because on top of that mass in stars, there's probably an even bigger dark matter halo, we call it. Dark matter is distributed generally on larger scales than the stars. The stars are at the center, and then there's a surrounding component of dark matter that we call the halo.
So it's not just a shell. You think that the dark matter is throughout the galaxy,
Yeah, it is.
but it extends much further out than the stars do.
That's exactly right.
What a strange distribution. Why would the dark matter behave like that?
Well, it's the other way around. It's that the stars sort of have sunk toward the center. At the beginning, they were, normal stuff, and dark matter were distributed in the same way.
Okay.
And then as normal stuff sort of undergoes processes and transforms itself into stars, generally sinks toward the center. So you have to think about, you start with a nice cake or something, and then all the raisins,
Have fallen inside.
Yeah, exactly.
Now, do astronomers have any kind of idea why there might be spirals and ellipticals? Is that like male and female galaxies? What's going on
Well,
here?
that's a big, big question, of course. And one that we're still trying to solve now. But I think so that's the overarching question. Why do galaxies have the shapes they have?
Right.
And most people think that galaxies are born as sort of disks or spirals, and then only by merging them, by doing giant cosmic collisions, you form these footballs.
Okay.
When you slam together two spirals, you can form something close to a football. But the real question is, how do you do that right? Because we can't end up with just any football. We know that galaxies have very specific properties. And one of the most puzzling, I would say, that we've discovered maybe in the last decades, is that every time you have a football galaxy and you look at the center, you find a supermassive black hole. And not just any supermassive black hole. The mass of the supermassive black hole is proportional to the mass in stars of the football.
Let's back up just for 1 second. Black holes.
Right.
Condensations of something, matter or energy, that are so dense that the speed of escape is greater than the speed of light from some surface that surrounds them. So these black holes do exist in these galaxies.
Yes.
But you're saying that they come in different sizes. They're not all the same thing. Why is something like that true? Why do we have very, very massive ones and less massive ones, as you've just implied?
Well, we don't know why.
Okay.
We know we've measured them. So we know that sometimes we find smaller ones, like 1 million solar masses,
Okay.
like the one in the center of our own Milky Way is a few million solar masses.
Okay.
And sometimes we find giant ones that are billions of solar masses
Okay, but there is a correlation with
with the mass in stars.
more stars, bigger supermassive black hole.
So good rule of thumb is about 0.2% of the mass in stars is in the black hole.
Now, how do you actually go ahead and measure the mass of a black hole?
That's a great question. And what I find fascinating about this subject is that I'm basically talking about invisible stuff. So both dark matters and black holes,
And dark energy.
nobody can see them. So
Any of it.
exactly. But yet we are here discussing their properties. and so on.
Correct.
So it's very similar to the way we measure the mass of the sun. We know Earth goes around the sun in a certain amount of time,
Right.
and we know it has a certain distance. So we apply Newton's gravity, and we can infer the mass of the sun at the center. And the same thing we can do for black holes. We have to choose objects that are orbiting around the black hole. And by studying their orbits, we can infer the mass of the object at the center.
So the more massive the object is, the faster something has to go
For example.
to keep from falling in
Exactly.
at a certain distance.
Yes.
And that gives you a handle on the mass of the
Yes.
black hole. Okay. And what sort of precisions can people actually measure the mass of the black hole? Are there errors of 50%, 100%?
It
Can you
depends
do
a
better?
lot on where you are.
Okay.
I mean, of course, in our Milky Way, things are more precise.
Yes.
But in the kind of environments I study that are typically very distant galaxies, I think sort of a good goal is to reach a factor of 3 uncertainty, which means that if I say an object has 1 billion solar masses in mass, it could be 3 billion or it could be 1/3 of a billion.
0.3 billion, okay.
But
you wouldn't want to build a bridge that way.
no, you
Not
wouldn't.
with that kind of error.
No, certainly not. But if you think that you're measuring black holes all half the way across the universe at billions of light years away,
Yeah. Not bad.
it's not bad. I would
It's
say.
certainly good enough.
Yeah, exactly.
Okay.
Yeah.
And you do see that strange correlation. So you
Yeah.
clearly want to understand why that's happening.
Right, and where it comes from.
Yes.
Because if you really believe the elliptical galaxies formed by smashing together spirals,
Right.
when you're do you form the black hole at the same time, or is it something that was in a spiral before?
Yes.
How does it know it and has to end up in a galaxy with that mass?
Yeah.
You don't know.
So what then is the outstanding question today, would you say, in the supermassive black hole and in the dark matter community, and what are the possible connections between them?
I would say, so there are many questions, of course, but I would say the overarching question is, how do we end up with the universe that looks the way it does?
Yes.
I mean, we know the universe started early on as a very sort of homogeneous fireball. There was something, you have to think of some sort of soup that was in equilibrium and all that. And now we end up with something that is very far from equilibrium. There are bright galaxies in an empty space. And these bright galaxies have supermassive black holes, colors, rich chemical composition. How do we end up with this? And we now know, I mean, maybe 20 years ago, people would not have included black holes in this picture. But we now know that black holes are a fundamental ingredient of this. And the reason is that even though they're small in terms of total mass, 0.2% of your mass, how much is that?
So
a few ounces.
Yeah.
Right? But what these guys do is when they accrete mass, they're extremely powerful sources of light. So when stuff falls into black holes, it releases so much energy that the black hole itself, the region around the black hole, can outshine the entire galaxy for brief periods of time. And so this giant source of energy, many believe, acts as sort of a thermostat. You know, when you're in a room like this, and you set the temperature to 71 degrees. If it gets too low, then the heater comes up and so on. And so black holes may be doing the same thing for galaxies. When the temperature of the gas in the galaxy is too low, this turns on the accretion disk around the black hole, and that heats up the gas again. And when it's too high, nothing falls onto the black hole, and the heating stops. And in some sense, that could regulate the way you heat and cool gas, which is ultimately related to the way in which you form stars.
So that suggests that you're going to have episodes when things are very hot or very active,
Yes.
and times when things are rather cold. You'll cycle up and down.
Yeah.
That's actually a prediction of what you just said. Do we have evidence that that is true?
Well, we certainly know that black holes have active phases and inactive phases.
Okay.
We've seen quasars, and those are active black holes, and we've seen plenty of quiescent black holes, and we have some ideas of the timescales involved as well. Then computing actual detailed predictions in terms of what this means, it's extremely challenging, because you have to imagine that you need to be able to solve a physical problem that goes from scales that are of order of a fraction of a light day to
The various centers of galaxies.
the very center, the very regions close to the black hole, close to the event
Very
horizon,
tiny. Yes.
to scales of tens of thousands of light years, including all sorts of crazy physics. So these are very challenging calculations to make. And so I think one of the interesting developments now is that people are starting to understand how to make these calculations and predict things that then we can test with our observations.
Now, you said that the black holes live right at the centers of the galaxies. That apparently is where they are observed. Why? Why do they prefer the center, the Times Square, if you will, rather than living out in the suburbs, in the outer part of the galaxies?
Because they're like, you know how if you sort of, if you put things of different sizes and masses together and then you shake the container, you generally end up with the heavier things at the bottom. So that in some sense happens to galaxies
A
as
kind of
well.
gravitational settling.
Sedimentation, that's
Okay.
some sort of.
And so that will put the black holes at the center,
Well,
more
let's
or
say
less.
that funnels mass in the center. That's where you tend to fall.
Now, you suggested also that when you crash spiral galaxies together, you'll end up with an elliptical. But if each spiral galaxy, like our own Milky Way, has a supermassive black hole in it, does that suggest then that the supermassive black holes are going to interact with each other?
Most likely, yes, and they're going to merge.
And become one even more
Yes.
supermassive black hole. Okay, so might that then suggest why, when you have more stars, you also have more
Yes, but it's not
supermassive
that
black
simple.
hole?
It's not that intuitive, because it's still up for, it's still being discussed, but many people believe that it's the round part of galaxies that correlates with the black hole. So if you start with two flat galaxies, you shouldn't really have the right mass of black hole to end up then with a giant elliptical. So that mechanism is certainly important, but we don't know exactly how it plays out.
Do we have an idea where the black holes came from in the first place? Do they predate the dark matter? Does the dark matter predate them? It's a kind of chicken and egg, isn't it?
Right, so that's one of the points of my talk, is that we really don't know which one comes first. We have some ideas. We think that there are seed black holes that grow, but the relative timing of the two. And our view of formation of structure in the universe is that things start small and then grow bigger and bigger. But we don't know the relative timing of the growth of black holes and galaxies.
Right.
And one of the goals of my research is figuring out the relative timing of that. So I look far, far away, that means back in the time, and I try to figure out who comes first.
Okay. And how supermassive a black hole have you been able to detect very, very far back in time?
So, well, me personally, it's not that interesting, but
Anyway.
astronomers in general
Yes.
have been able to find black holes that are billions of solar masses, and they are some of the most distant objects known.
So they were there early on.
At least some supermassive black holes were there very early on.
Could they conceivably have emerged from the Big Bang? Is that at all possible?
As they are now, I would say that's unlikely. Most people believe they've grown.
Okay. So they're probably not primordial, not
not-
right from the very
They're not
beginning
like big chunks of
of the Big Bang.
Of Big Bang, yeah.
Okay.
Probably
that
not.
didn't bang.
Yeah, but who knows? I mean,
Yes.
it's good to keep an open mind on these things.
Okay. 5 years from now, what question do you hope that you and your colleagues who also work in this field will have been able to either answer or at least have made significant headway on?
Well, 5 years is, I mean, I probably will not be completely wrong, but I would say that I'd love for us to have a candidate dark matter particle, something that, you know, we have detected and could be the dark matter particle.
Yes.
I'd love if we were able to know when black holes formed relative to galaxies, who formed first, and how do they play with each other. See, that's not really a binary question. That's not really a question that has a definite answer. So it's not like the dark matter candidate that you know you have it.
Either
Here
you do
is
or
a
you
more
don't.
open question.
Right.
But I think in 5 years from now we'll have a much better idea of
Okay.
that. And yeah, I would say those are the two most interesting questions on that area.
And now I'll ask you a more difficult question. Where do you think the answers to these questions will come from? If you were a betting man, which telescope, imagine you are for the moment, which telescope, which technique would you place your money on as being the place most likely to give us that breakthrough? A nearly impossible and very unfair question, but I'll ask it anyway.
As a scientist, the only thing I know is that the answer is always unexpected. So I can tell you something and it will be wrong. So it will come from a telescope. That's probably my safest statement.
But there's really no way of knowing, and that's why astronomers hedge their bets.
Exactly.
That's why they try optical, radio, infrared, gamma rays, the whole spectrum. We're greedy. We are greedy.
No, it's not that we're greedy. I think that one of the things that we have to emphasize is that this is not like a lab experiment. It's not that we are making our universe in a little box and we can turn it around, turn it on and off and all that.
Right.
We only have one universe.
Yeah.
And we're looking at it from a very unfortunate direction. And so we have to use all the information we can get. Sometimes that information is optical light, sometimes it's radio light, sometimes it's gravitational waves, sometimes it's neutrinos. So we have to use all these different sources of information to put together a puzzle. And it's hard, but that's what makes it fun.
Do you ever think about doing anything else, or is astronomy utterly in your blood? Is this the thing to do?
Well, I'm having fun so far. So I would say for the moment I'll do astronomy, but who knows, maybe in 10 years I'll do something else. But for the moment, I think this is so much fun that I want to keep doing it.
Wonderful. Thank you so much for a great interview. It was a real pleasure.